When a new AI application lags, the immediate instinct for most engineering teams is to blame the model itself. They assume larger intelligence or more powerful GPUs are the only cure. This leads to wasted budgets and frustrated developers who never touch their actual codebase. But what if I told you that cutting response time from 90 seconds down to 4 had nothing to do with the model's brain? What if the bottleneck wasn't in the algorithm at all, but in how we feed it data? Today, we are dissecting a real-world case study where shifting from serial fetching to parallel hardware utilization solved what everyone thought was an intelligence problem. The core issue here is often described as a synchronous trap. In traditional retrieval-augmented generation pipelines, systems frequently operate like a chef who waits for every ingredient to be chopped before starting the fire. The system fetches one piece of information from a database, processes it, and then moves on to the next step only after that specific task completes. This creates massive dead air where expensive inference hardware sits idle while waiting for input-output operations to finish. The model is ready to compute, but the data pipeline has stalled. Modern systems engineering flips this script by decoupling retrieval from generation. Instead of one stream at a time, we utilize concurrent processing streams that keep the compute units saturated rather than starved by wait states. This shift transforms information access systems from simple text generators into true information synthesis engines, where latency is dictated by flow efficiency, not raw model capacity. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This architectural flaw explains why teams see massive spikes in response times without any code changes on their part. Recent telemetry across major platforms reveals a pattern of systemic degradation rather than algorithmic failure. For instance, API calls for advanced models jumped from under 4 seconds to over 11 seconds due to back-end processing shifts that isolated the issue to inference batching failures. Similarly, users reported incredibly slow output and memory leaks affecting roughly 33% of deployments on high-end hardware, despite having ample RAM available. These are not bugs in the model logic, they are bottlenecks in how the client-side agent orchestrates calls to the backend. When latency triples or extends into minutes across different environments without code changes by the user, it indicates that the infrastructure is failing to keep up with the speed of modern inference engines. The fix requires engineering optimization at the orchestration layer, not scaling the model itself. There is a deeper psychological factor driving this misdiagnosis as well. A behavioral study involving over 1,300 participants revealed a significant bias where users treat AI predictions as infallible authority. In experiments, more than 40% of participants accepted an AI's output even when it meant forgoing guaranteed rewards or better solutions because they trusted the system too much. This tendency translates directly into engineering decisions. Developers assume a larger model is the only fix for slowness because they trust the heuristic that size equals speed and intelligence. The data shows this bias leads to significant operational costs, with earnings reductions ranging from 10.7% up to 42.9% among those influenced by perceived AI authority. When we treat the system as an oracle rather than a pipeline of components, we overlook the simple plumbing issues causing the lag. The solution lies in re-evaluating your data flow patterns before requesting new hardware or larger models. You must audit whether you are fetching data serially and if your vector database is blocking inference operations. The gain from shifting to asynchronous processing comes entirely from keeping compute resources active during I/O wait times, turning idle cycles into productive throughput. By focusing on system orchestration and parallel utilization, engineers can achieve dramatic latency reductions without changing a single line of model code or upgrading expensive GPU clusters. This approach saves companies money that would otherwise be wasted on unnecessary hardware upgrades while delivering the performance users actually need for their applications. The engineering trade-off is clear. Asynchronous input-output operations over synchronous fetching provide superior scalability and responsiveness. Vector search optimization strategies further amplify this by ensuring that retrieval happens in parallel with generation, rather than as a blocking step before it begins. This paradigm shift moves the conversation from asking why an AI response is slow to analyzing how we are feeding the intelligence engine. It requires a fundamental change in perspective. where the pipeline architecture takes precedence over model size assumptions. Understanding these system orchestration principles makes you more valuable than simply knowing how to prompt a larger model. The ability to optimize data flow and identify bottlenecks saves organizations significant compute costs that would otherwise be burned on ineffective scaling strategies. By prioritizing production trade-offs and practitioner decisions, we can build systems that are not just powerful but also efficient and reliable in real-world deployment scenarios. This is the difference between a team that chases bigger numbers and one that engineers better performance through architectural insight. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.